Hello students, welcome to Educate. In previous lecture we have studied that electric field due to long straight charged wire is given by E equal to E equals lambda upon 2 pi epsilon naught R. Today we are going to study electric field due to uniformly charged infinite plane sheet. Here in this diagram, this is the uniform plane charge sheet which contains positive charge on both sides. So here we consider an imaginary, either we can consider a cube or we can consider a cylinder. Both will serve the purpose. So here this is imaginary cube. So if we consider its this face, so what do we observe? Area of this face is say A, and its unit vector, area vector will be in this direction. Suppose we write n cap, and electric field is also in the same direction. So what is theta here? Theta is 0 degree, and you know that flux phi E is given by E ds cos theta. Here area is certain, so we don't have to use integration. We will say EA cos 0 degree, and that will give 1. So flux through this face is EA. Here if you consider this face, so electric field will be in this direction, but area vector will be in this direction. So it will make angle 90 degree, so no flux. Similarly, from the lower face, same will happen. From the face that is facing to you will also have no contribution in the flux. Similarly, opposite face will also have no contribution. So here there is another face in which electric field is in this direction and area vector is also in this direction. So here also flux phi E, if you write here 1, if you write it 2, so it will be same. So total flux phi will be sum of the two, that is 2EA. And you know that phi is Q upon epsilon naught. So 2EA. Here our concern is to get E. So E will be equal to Q upon 2A into epsilon naught. But if you remember, I told you about surface charge density sigma. Sigma is given by Q upon A. So this becomes sigma divided by 2 epsilon naught. If you want to make it in vector form, then here you can add n cap. So this is how we can calculate electric field by using Gauss law. Here we have made the use of Gauss law, that flux phi equal to charge enclosed divided by epsilon naught. So let's read it here also. So the same thing is given here, 2EA equal to sigma A upon epsilon naught. So EA will cancel out. In place of charge they have written sigma. I can tell you this thing also, what they have given. So the same thing, Q upon area is sigma, or in place of Q we can write sigma A. Same thing is written here. So we will get same result. Now here direction of E is given. E is directed away from the plate if sigma is positive, and towards the plate if sigma is negative. Note that the above application of the Gauss law has brought out an additional fact, that is E is independent of X also. Here X term is not involved. you will see that suppose there are two plates, and here if this is say positively charged, means the charge density is sigma plus sigma, you can write here also it is plus sigma. Then what happens if you find electric field here in this region, in this region, in this region? So there are three regions possible. So here electric field will be minus sigma upon 2 epsilon naught due to this plate, and due to this plate also it will be minus sigma upon 2 epsilon naught. So this will become minus sigma upon epsilon naught. If you consider this middle region, so here field due to this plate will be sigma upon 2 epsilon naught, and due to this it will be minus sigma upon 2 epsilon naught. So this will give 0. And if you consider region number 3, so there electric field will be sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which will give 2 sigma upon 2 epsilon naught, which is equal to sigma upon epsilon naught. Now see another situation when these plates have charge densities of opposite nature. Suppose one plate has charge density sigma plus with plus sign, another plate has charge density minus sigma. Now if you consider this region and this region, then what will be electric field in these regions? So here due to this electric field will be minus sigma divided by 2 epsilon naught, and due to this minus sigma it will become plus sigma divided by 2 epsilon naught. So here in this region electric field will be 0. Now if you consider this region, so what is electric field? So sigma upon 2 epsilon naught due to this, and due to this it will be again sigma upon 2 epsilon naught, because field will be in this direction, and due to this also along same line. So it will become sigma upon epsilon naught. And what about third region? If you consider this region, so field due to this will be sigma upon 2 epsilon naught, and because of this field will be in this direction. Because of this field will be in this direction, because of this field will be in this direction. So again it will get cancelled. So this will become sigma upon 2 epsilon naught, giving the field to be 0. So you have seen different cases. You can take both plates negative also, then you will see the result like this. Suppose here this is minus sigma, this is minus sigma. So region 1, region 2, region 3. And if you evaluate the field first region, so it will become sigma upon 2 epsilon naught, and due to that also sigma upon 2 epsilon naught. So it will become sigma upon epsilon naught. If you consider this region, what happens? So minus sigma upon 2 epsilon naught and plus sigma upon 2 epsilon naught. This will give 0. And if you consider this region, then what happens? Minus sigma upon epsilon naught minus sigma upon 2 epsilon naught, giving minus sigma upon epsilon naught. So these are three possibilities, and you have understood how to evaluate. We will do some numerical questions based on these concepts, so it will become clearer, or other things related thereto we will study. Now we are going to study field due to a uniformly charged thin spherical cell. Here you are given, this is a spherical cell, contains surface charge density sigma, and we have to find out electric field at different points. If we consider electric field at this point, so for that we have to consider a Gaussian surface. Gaussian surface will enclose this charge, and because of spherical symmetry, we can assume that total charge is concentrated at this point, and then we can apply Gauss law to calculate the field. So here EA equal to charge enclosed and surface charge density is given. So we can get E into A. If you are considering this sphere of radius r, so its surface area will be 4 pi r square, and the total charge sigma times, you can calculate it for radius r, what is total charge. So here the same thing is given. So charge enclosed will be sigma upon epsilon naught, and total charge if you want to calculate, so for that you just multiply 4 pi r square. So here let's read it. Consider a point P outside the shell with a radius vector r. To calculate E at point P, here we want to calculate, we take the Gaussian surface to be a sphere of radius r and with a center O passing through point P. All points on this sphere are equivalent relative to the given charge configuration. This is what we mean by spherical symmetry. The electric field at each point of the Gaussian surface therefore has the same magnitude E and is along the radius vector at each point. It's very obvious. So whether you take at this point or at this point, electric field will be directed outward. This is positive charge. Now, therefore has the same magnitude E and is along radius vector at zero. Thus E and delta S at every point are parallel. So theta will be 0 degree. And the flux through each element is E into ds or delta S. Summing over all delta S, if we find sum of delta S, that will be just surface area. The flux through the Gaussian surface will be E times 4 pi r square. So charge enclosed will be equal to sigma times, because sigma is charge density, sigma times surface area on which the charge is distributed. So charge will be this much, sigma times 4 pi r square. So here we write it. So what do we get? E times 4 pi r square equal to sigma times, this is charge, 4 pi r square divided by epsilon naught, or E will be equal to, here we can simplify. So sigma 4 pi will cancel out, and then epsilon naught will be left. So r square divided by r square. Now in place of sigma, what we can write? Sigma equal to, Q equal to 4 pi r square sigma. Here we can write, we can multiply here 4 pi r square sigma. So 4 pi will appear in denominator also, and then we will get this relation. So we can say E will be equal to Q upon 4 pi epsilon naught r square, and if we want to make it in vector form, then we write vector E equal to Q upon 4 pi epsilon naught r square r cap. So if charge is positive, here electric field is directed outward if Q is greater than 0, otherwise it will be inward in case of negative charge. So this is the relation that we have got. Now we have got the relation E equal to Q upon, in magnitude I am writing 4 pi epsilon naught r square, where r is, this is cell, and r, small r is like this, point was taken here. Now at the surface, this small r will be replaced by capital R. So small r equal to capital R, if we write, then we will get E equal to Q upon 4 pi epsilon naught r square. This is basic relation that you have studied due to point charge. Suppose charge is centered here, suppose this is sphere and charge is placed here. In that case, at distance r, so we can find electric field. So this is basic relation. Now further, it recalls you that suppose charge q is here, and at certain distance if you want to find out electric field, so you use q upon 4 pi epsilon naught r square. The same is happening in case of here spherical charge distribution is given. We have taken surface charge density sigma, so we have got the same result. Now suppose we consider any point inside this surface where charge is distributed. So what do we get? Suppose we are here at point P and charge is outside. So if we consider a Gaussian surface here, it will enclose no charge. So in that case, this relation means E equal to Q upon 4 pi epsilon naught R square will become 0. So inside this surface, electric field is 0. At the surface, electric field is this, and outside the surface, electric field will vary with small r. So if we plot a graph between electric field and distance, so what do we get? Distance varies in this direction. So till here, when small r becomes capital R, at this point small r and capital R both are equal. At that point, suppose electric field is here, E equal to Q divided by 4 pi epsilon naught R square. But since small r equal to capital R, so this will be capital R square. And as you move away from the center, so this r will start increasing. So our relation in that case will be E equal to Q upon 4 pi epsilon naught small r square. So we can say that strength of electric field will be like this. So here E proportional to 1 upon r square. I think you remember the graph of y equal to 1 upon x square. Y equal to 1 upon x square has graph like this. Now let's go to next topic. Here there is one question. The question is, an early model for an atom considered it to have a positively charged point nucleus of charge Ze surrounded by a uniform density of negative charge up to radius r. The atom as a whole is neutral. For this model, what is the electric field at distance r from the nucleus? So here the entire charge, positive charge, is concentrated at this point. Positive charge is here and negative charge is distributed throughout the volume. So at this point, if you consider what is net charge, so JDE is total positive charge and minus JDE will be total negative charge. So net charge will be 0. That is why an atom is neutral. Now suppose we consider any point here inside, then what happens? If you consider this sphere, in that case what will be total positive charge and what will be total negative charge? So here total positive charge will remain JDE, but negative charge will decrease because in volume 4 by 3 pi capital R cube, total negative charge is minus ZE. Now if you are considering small radius, small r, so in that case here you can say negative charge per unit volume, it will be equal to minus ZE divided by 4 by 3 pi capital R cube. Now here you are considering a small sphere of radius small r. In that case negative charge enclosed by sphere of radius small r will be, suppose that is q dash equal to minus ZE divided by 4 by 3 pi r cube multiplied by volume of that small sphere. So 4 by 3 pi small r cube. So 4 by 3 pi will cancel out, and we will be left with q dash is minus ZE times r cube divided by capital R cube. Small r cube divided by capital R cube. So this is total negative charge enclosed. So if we find net charge, so ZE minus Q dash, so ZE minus ZE times R cube divided by capital R cube. So this is net charge, say Q. So here ZE can be taken common, 1 minus R cube divided by capital R cube. So this is charge. Now if we want to find out electric field, then we can apply the formula that electric field E equal to charge this Q divided by 4 pi epsilon naught and distance square R square, and we can put this value. So we will get electric field. Suppose we want to find out flux. So phi equal to Q upon epsilon naught, but you have to take Q this value. Now consider another situation in which point P lies outside. In that case, what will be electric field? Suppose point P is here, this distance is smaller. In that case, what will be electric field? What will be total flux? So here, positive charge, net positive charge will remain ZD, net negative charge will be minus ZD. So charge enclosed will be 0. If charge enclosed is 0, it means no flux, no electric field. So only field is limited inside. On surface also the same thing will happen. Net positive charge and negative charge will cancel out and nothing will be left, so no flux. So you have seen the situation as discussed in the question. Now here there are certain questions. What is the force between two small charge spheres having what is the force between two small charged spheres having charges this much are placed 30 centimeter apart? So here force equal to, Q1 Q2 divided by 4 pi epsilon naught R square. You can put the values. So it will become 9 into 10 to the power 9 into Q1 Q2 2 into 3 into 10 to the power minus 14 divided by distance square 0.3 square Newton. You can evaluate. Then next question is the electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. What is the distance between the two spheres? What is the force on the second sphere due to first sphere? So here again you are given two charges, separation is to be found, so it is R. One is 0.4 microcoulomb, another charge is minus 0.8 microcoulomb, and the force is given as 0.2 Newton. Apply formula again. So 0.2 equal to 9.9 into 10 to the power 9 into values of charges 0.4 into 0.8 into micro means 10 power minus 6 minus 12 divided by separation square. You can take r square here, 0.2 here, and then take square root to get the distance. That is simple. Now, second point, what is the force on second sphere due to the first sphere? Rule is very simple. To every action there is equal and opposite reaction, so force will be same. Now, next question is, check that ratio Ke square upon GMEMP is dimensionless. Look up a table of physical constant and determine the value of this ratio. What does this ratio signify? Here, if you remember Coulomb's force, suppose we write it F electrostatic. So this is suppose proton and electrons are there. Proton and electron. So charge on both will be E and E, and separation between them is say R. So force will be 1 upon 4 pi epsilon naught times E into E, that is E square, divided by separation R square. Here we can take this as K. So K E square divided by R square. This is electrostatic force. Now, if mass of proton is mp and mass of electron is me, then we calculate gravitational force Fg is g times mp into me divided by r square. This is also force. This is also force. It is in Newton. This will also be in Newton. Now let's divide the two. So Fe divided by Fg will be equal to r square will get cancelled and we will get Ke square divided by g times mp into me. If we write the units Newton upon Newton, so Newton upon Newton will cancel out and we will get this quantity as dimensionless quantity. So here check that the ratio Ke square divided by GMEMP is dimensionless. It is established. Now look up a table of physical constants and determine the value of this ratio. Let's see if we put the values. So K is 9 into 10 to the power 9 into electronic charge square 1.6 into 10 to the power minus 19 whole square divided by G 6.67 into 10 to the power minus 11 times mass of proton 1.66 into 10 to the power minus 27 multiplied by mass of electron 9.1 into 10 to the power minus 31. If you evaluate it, it will give a very large quantity. So what does it signify? It signifies that electrostatic force is much larger as compared to the gravitational force. Now, next question says, explain the meaning of the statement electric charge of a body is quantized. We have already studied about quantization of charge, that charge Q is integral multiple of electronic charge. It can't be in fraction. Although it is possible, when you study quark theory, you will find that discharge can be written in terms of up, down, different type of quarks are there, but that is not in your syllabus. So you should assume that Q equal to NE only. So that thing is given here. Why can one ignore quantization of electric charge when dealing with microscopic? Microscopic and microscopic. You understand? Microscopic means on small scale. Number of electrons can be counted. Electrons can be counted On the other hand, if it is microscopic, then number of electrons will be very large. They will become almost uncountable. So that is why we say, why can we ignore quantization of electric charge when dealing with wax? So this is the reason. When we deal with microscopic level, in that case number of electrons are very large, so we can't use this quantization concept. Now next question is, when a glass rod is rubbed with a silk cloth, charges appear on both. A similar phenomena is observed with many other pairs of bodies. Explain how this conservation is consistent with the law of conservation of charge. Explain how this observation is consistent with the law of conservation of charge. So let's see what happens. Suppose there is one body here, another body here. If the two bodies are rubbed against each other, so electrons being lighter, they get transferred. Suppose X electrons are transferred. So total charge will be minus XE on this body. Same number of positive charge, means same amount of positive charge will be developed here, XE. What was the situation in the beginning? The two things were neutral, and now if you again add these two charges, then what will you get? You will get 0. So that is why here law of conservation of charge holds good and there is no violation at all. Next point is 4-point charges QA, QB, QC and QD are located at the corners of a square ABCD of side 10 cm. What is the force on the charge of 1 microcoulomb placed at the center of the square? So let's see how to calculate it. So you are given a square in which 2 microcoulomb minus 5 microcoulomb, then 2 microcoulomb, then minus 5 microcoulomb. Charges are there. We can do ABCD here, A, B, C and D. What is the force on a charge of 1 microcoulomb placed at the center of the square? 1 microcoulomb charge is placed here. 1 microcoulomb. Correct. Now, if you find this distance, here side is 10, this is 10, this is 10, this is 10 in centimeter, this is 10. So this point will be equidistant. So we can calculate it. This is x, this is x, this is x, this is x. How to evaluate x? So it is simple. This angle will be 90 degree because this is a square. This angle is 90 degree. Then you can apply here. This is 10, this is 10. So if you apply Pythagoras theorem, this side will be 10 root 2 and this point will be midpoint of it. So it will be 5 root 2. So value of x is 5 root 2 centimeter. Now, this is positive charge, this is negative charge. So what will be the direction of force due to this 5 microcoulomb charge on 1 microcoulomb charge? So this is positive, this is negative, so force will be in this direction. So if we evaluate F1, so that will be 1 into 5 into 10 to the power minus 12, 1 microcoulomb, 5 microcoulomb into 9 into 10 to the power 9 divided by separation square 5 root 2 whole square multiplied by, it is in centimeters, so 10 power minus 2 square should also be multiplied. So you have got F1 whose direction is along, suppose this is, if you take this point P, so you can say along PB. Now Let's consider force due to this minus 5 microcoulomb on charge 1 microcoulomb placed at point P. So its direction will be, in this case, it will be like this because of this negative charge. If this body is free to move, so it will move in this direction. So F2 will be same, everything is same because here distance is x. So same value we will get, but direction will be along PD. So what will happen? Two equal and opposite forces are acting on 1 microcoulomb charge. So net force due to this minus 5 microcoulomb charge and this minus 5 microcoulomb charge will cancel out. So this portion is done. Now consider force due to this 2 microcoulomb charge on 1 microcoulomb charge. This is positive, this is positive. If this is fixed, then what would this do? It will move away. So force will be in this direction. We can calculate its magnitude again. Similarly, if we assume that this 2 microcoulomb charge is fixed and this is free to move, then it will move in this direction. So again we will get another force. So if we evaluate F3 and F4, both will have same magnitude, but their direction will be just opposite. So again the two will get cancelled out. Hence we can say that no net force on this 1 microcoulomb charge will act. So this is the question. The question was 4 point charges QA, QB, QC and QD located at the corners of a square of ABCD of side 10 cm. What is the force on a charge of 1 microcoulomb placed at the center of the square? So our answer is, it will be, there will be no force. Consider next question. Next question says, an electrostatic field line is a continuous curve. What is a field line? That is, a field line cannot have sudden breaks. Why not? It is simple. Suppose you write the relation E equal to Q upon 4 pi epsilon naught R square. And if you plot a graph between E and R, will it be zero suddenly? Is it possible? Graph will be like this. But value of this E will never be zero. It will try to touch this R axis, but at infinity. So same thing is given here. It says that, where is the question? An electrostatic field line is a continuous curve. So this is logic. So field lines will be continuous and they cannot have sudden break. If sudden break happens, it means what? Field is suddenly zero. It means R has become infinity. Suddenly R can't become infinity. So that is not possible. Then next question is, explain why two field lines never cross each other at any point. Again same thing will happen. So suppose this is one field line and this is another field line, and we imagine that they are intersecting each other at this point. So at the point of intersection, what will happen? Here if we draw the tangent, so this tangent will indicate that field at this point is in this direction due to this field line. Now we consider this field line and again we draw the tangent at this point, at the point of intersection. So field will be in this direction. Is it possible that due to a charge at one point there will be two directions of electric field? It is never possible. Now 2 point charges QA, QB are located 20 centimeter in vacuum. What is the electric field at the midpoint O of the line AB joining the two charges? So let's calculate it. You are given 3 microcoulomb minus 3 microcoulomb, and this separation is 20 centimeter. And what is electric field at the midpoint? So we are taking this point P. This is 10 cm, this is 10 cm. At this point we have to find out electric field. So this is point A, this is point B. Now due to this positive charge, electric field will be like this. So let's evaluate E1. E1 equal to Q. So 3 into 10 to the power minus 6 into 9 into 10 to the power 9 divided by distance square 0.1 square and directed along AP. Now we find electric field due to minus 3 microcoulomb charge. This is negative side. So it means field will be in the same direction. So E2 will be same 3 into 10 to the power minus 6 into 9 into 10 to the power 9 divided by 0.1 square and direction will be PB, along PB. So since both fields are directed along same line, so here total electric field will be sum of the two, twice of any one. 3 into 10 to the power minus 6 into 9 into 10 to the power 9 divided by 0.1 square and direction will be same. So from A to B. Now if a negative test charge of magnitude 1.5 into 10 power minus 9 coulomb is placed at this point, what is the force experienced by this test charge? So it is simple. Either whatever value of electric field you have found, just multiply this test charge to that value, you will get the force. Or you can calculate separately the force on this charge due to other two charges. So I am going to show you how to calculate, although full calculation I will not do. So here suppose we take this as 3 microcoulomb and another is say minus 3 microcoulomb, and this is midpoint where negative 1.5 into 10 to the power minus 9 coulomb charge is kept. Here what will happen? Due to this charge, force will be, what will happen? Force on this is to be found. So you can keep this charge as constant. Suppose this is stationary and you will observe the motion of this charge. So if this charge is free to move, then it will move in this direction. So E1 you will calculate. So E1 will be equal to how much? E1 will be not even, sorry, we are calculating force this time. So F1 is equal to 3 into 10 to the power minus 6 into 1.5 into 10 to the power minus 9 into 9 into 10 to the power 9 whole divided by 0.1 square, and the direction of force is, say this is P, this is A, so along PA. Now here if you keep this charge fixed and this charge is free to move, then because of repulsion it will move in this direction. So if you calculate F2, so that will be equal to 3 into 10 to the power minus 6 into 1.5 into 10 to the power minus 9 into 9 into 10 to the power 9 divided by 0.1 square, and its direction will also be, suppose you write here B, so along BP. Since both forces are in same direction, so net force will be sum of the two forces. So F1 plus F2. You can get this way also. Now we are going to consider next question. A system has two charges QA, QB located at points 0, 0, minus 15 centimeter and 0, 0 plus 15 centimeter respectively. What are the total charge and electric dipole moment of the system? So here 3D points are given. So this point is on Z axis, this point is also on Z axis. So I'm just drawing Z axis and I'm locating the points here. One is minus 15 cm, another is plus 15 cm. So what is total length? Separation. So we write it as 2a. 2a will be 15 plus 15. That is 30 centimeter or 0.3 meter. What is charge? Charges are equal and opposite. So here we have to find out dipole moment P equal to 2aq. We take positive charge for this purpose. So 0.3 is 2a and the charge is 2.5 into 10 to the power minus 7. Unit will be coulomb meter. So this is dipole moment. Now if you find total charge, so total charge QA plus QB. So one is positive 2.5 into 10 power minus 7 coulomb, whereas another is negative minus 2.5 into 10 power minus 7. So total charge will be 0. There is another question. An electric dipole with dipole moment this much is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 power 4 Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. So if you remember, I told you how to find torque on dipole. Suppose this is electric field and here suppose this is dipole. There is positive charge, there is negative charge, and suppose this is A, this is B. So this distance is 2a and draw perpendicular, and this separation if you find, so this is 90-degree angle, and here force in the direction of electric field will be QE. Here there will be another force on negative charge, that is minus QE, and this is perpendicular distance. Torque is given by force into perpendicular distance. So here what is force? Force is QE into perpendicular distance. If this angle is theta, so this will be, this distance is needed, so this will be 2a sine theta. So here you can write 2a sine theta. Now whether this expression is serving the purpose or we need simplified version, we can see an electric dipole with a dipole moment. Value of dipole moment is given, and you know 2aq gives a dipole moment. So here we can write it as Pe sine theta. Now P is given, E is given as 5 into 10 power 4 and theta is given as 30 degree. So we can put that value over there to get the value of torque. Now there is another question. A polythene piece rubbed with a wool is found to have a negative charge of this much. Estimate the number of electrons transferred from which to which. So as you know, if there are two bodies and one is rubbed against another, so electrons get transferred. Suppose electrons are moving in this direction. So here there will be positive charge and here there will be negative charge. So here charge is given that 3 into 10 power Q equal to 3 into 10 to the power minus 7 Coulomb. You have to find out number of electrons transferred. So you can apply Q equal to NE 3 into 10 to the power 7 negative sign equal to N times electronic charge 1.6 into 10 to the power minus 19. Then N equal to 3 into 10 to the power minus 7 divided by 1.6 into 10 to the power minus 19. Then calculation is your part. Now, second part says, is there a transfer of mass from wool to polythene? If electrons are being transferred, even if they have negligible mass, but of course there is transfer of mass. Thank you, Team Educate.